Hello everyone, welcome to the channel. So today we are going to implement closed form equation of linear regression. So first is the hypothesis. So y equal to bx plus e. Y is the output vector, b is the parameters that we need to find using the closed form equation, x is the input vector and e is the Gaussian error. So this is the equation. So b equal to x transpose into x inverse into x transpose into y. So first we are going to implement this. So before starting, I want to mention certain things. Like first, we will start with a very simplistic model, and then we add the enhancement to it. Like we have to add provision for intercept, then we have to add for singular matrices. So and then there is finally like elegant way we can optimize this whole closed form equation. We will discuss one by one. So first, let us import numpy. So class linear regression self. So self dot coefficient, this is the parameters that we are going to find, which will be none for now. So next we are going to create a fit method. So in the fit method, we will pass x and y. So now we will implement this equation. So self dot coefficient equal to, so we can't use inverse like this. So we have to use the class from numpy module, so linear algebra dot inverse. So this is the equation here, we have implemented it. Predict x into self dot coefficient. So this is the very simplest form of this equation. Let's see if this actually works. So I'm importing a dummy data set, which is a diabetes database data set. So here you can see I have split the data set into a training data set and test data set. So now let us create a model. Model dot fit. So predict equal to model dot predict x test. So let us print the predicted value and see if it works. Okay, I will name the linear regression as CF, just to, because we are going to compare with the scikit-learn model, so just to have a difference in the name, to not get collided with each other. Okay, we are getting some output. Let us verify if this output is correct. So we are going to import from scikit-learn, import linear regression. So model equal to linear regression. So it will be a same as this. So I am just going to copy paste it. Okay, so this is the actual value. As you can see, we are getting 139, 179, 134. Our actual output is nowhere near that. So there is some mistake in that. So now let us go back to the original hypothesis and the closed form equation. So if we look at the equation, we haven't added any intercept form to the normal equation. So that's why the model is severely underfitting, because we are trying to fit a baseline that passes through the origin. But our actual input data is not, doesn't necessarily need to follow that. They are not zero centered. So we need to add a, like we need to add a intercept line to the input vector. So that intercept acts as the bias of the model. So it helps in shifting the best fit line to fit the input vector. So first, let's add a parameter called fit intercept. Its default value will be true. There are scenarios when you can pass the value as false. I will explain that scenario too. So we will have a variable to store the intercept value. This will be the bias that shifts the best fit line. So we can have it as 0.0 for now. So we need a special method called add intercept. So if fit intercept variable is set to true, we have to add a feature column vector of filled with ones. Suppose dimension of x is m into n, our intercept vector will be m into 1 filled with zeros, filled with ones I mean. Is equal to np dot ones x dot shape 0, 1. So we are fetching the 0th value from the x shape, which will be the number of data points m, and we just need one column. That's why the value is 1 here. So we have to return it. So self will take x as input. So we have to like stack this feature column vector with the existing input vector. So we have to stack np dot h stack once x. So if the fit intercept variable is set to false, we just need to return the x as it is. So in the fit method, when we receive x, we have to pass it to the add intercept method. So this equation will remain as it is. So here we can change the variable to parameters. So if the fit intercept variable is set to true, we have to split the parameters into intercept and coefficients. So intercept equal to parameters first value. This first column will be the intercept column. The remaining columns will be the coefficients. If the variable isn't set to true, we can just assign entire parameters to coefficient variable. So while predicting, we have to add the intercept variable to the input vector calculation. So this should work now. So let's run the code. Okay, so we have an output using the latest code. So it's 139, 179, 134. So as you can see in scikit-learn 2, the values are 139, 174, 134 and so on. So the values are exactly identical now. So our code works. So in our code, we have used inverse class from linear algebra module. So this expects an x which is invertible. If it's not invertible, this code will fail. It throws an error. But in linear regression, we will have instances where the input vector might be singular matrices. So in scenarios when m is less than n, so m is the number of data points and n is the feature vectors, or in cases of multicollinearity. So in such scenarios, x might be non-invertible. So we need to have some mechanism that handles for that scenario as well. So there is a function called least square error. So this is what they have used in scikit-learn. We are going to use that too. So what it does is that it computes the vector x that approximately solves the equation a into x equal to b. So as you know, our hypothesis is that y equal to b into x. So A in our scenario will be X, B will be the output vector Y. So I will just copy paste this. So we just need to pass the input and output. So let's run. So let's run this code. Okay, so one thing to note is that it returns 4 values. One is X, which is the solution. Next is the residuals, rank, and singular values. We just need parameters alone. That is the solution. So I will just take that parameter alone. Okay, so solution, the prediction from our coded module and scikit-learn module are same. You can see the first value is 139.5475. The same is for scikit-learn. The last value is 166.254. It's same as 166.254. So now our code works exactly as the scikit-learn, but there is still one more optimization that we can do. So currently we are adding a column vector of ones. So it increases the dimension, it also increases the memory, it also causes non-essential multi-collinearity. So these are the issues currently in our code. So we can do a elegant way to do the calculation to find the intercept and coefficient. So I will explain with an example. So I will just copy paste this code. So this is a sample input and output vector. So I have done the exact steps that we did earlier. So I have added ones and stacked the columns, and then I found the inverse and then slope and intercept. This is same as the earlier. I'm just using this as a reference. Now I will find the new method that we are going to do. We are going to zero center both x and y, and then we find the slope from that, and then later we can use the means and the slope, and then we can interrupt the intercept. So let's see how we can do that. So x mean y mean equal to x dot mean y dot mean. So now we have to zero center it. So now we have to find the slope from it. So another thing is we have to reshape it, because it's currently 0 dimension. We need to convert it into 1 dimension. So this will be the slope. So you got the same slope as earlier. So now we need to find the intercept. So formula to find the intercept is y mean minus slope into x mean. Zero point 0.1 is the same as the earlier method. So now we have found both intercept and slope without adding an extra column. So this is much more elegant, and this is the way they have implemented in scikit-learn. Now we can implement this in our code. So now we have to do the changes to our code. We are going to remove the adding the intercept part, and we are going to zero center the inputs. So I'm going to just remove this function. We don't need it. Also, we don't need this line. So if the fit intercept variable is true, we have to zero center the input and output. So x equal to x minus x dot mean y equal to y minus y dot mean. So we are going to find the average across the column. So x is equal to 0. So you can just give the name xc yc. So now we have to find the solution for this equation. So we are going to pass xc and yc. So now we will have the slope of the function. So from the slope we can find the intercept, that like the example I showed you. So y mean minus x mean into self dot coefficient. So if there is no fit intercept method, we can just assign the parameters to coefficient directly. So now we have found the slope and also the intercept. So the predict method will be same as earlier. So now this should work as expected. So we can rerun this code. Okay, so it should be self dot fit intercept. Okay, so it should be capital X. Yeah, my bad. Okay, now we have gotten the output for the latest optimized version, and the output is same as the scikit-learn 139.54. It's the same as 115, same as scikit-learn. So we can even check it further. So as you can see, it's exactly the same as. So now we have implemented linear regression in its closed form equation. I just want to explain one thing more. So we have so far done the experimentation with just a fit intercept equal to true. Let us see what happens when fit intercept equal to false and where should one use that. So I will just enter false. Okay, I have some error. Okay, yeah, I should find the solution for when the case is fit intercept is not set as true to. Here it is just x and y. Yeah, now I think it should work. Okay, so let's print the output. Okay, so as you can see, the values are off by so much. The model is actually underfitting. It does not trying to fit the correct value. The thing is, the best fit line is trying to pass through the origin, so we won't get the correct data. So when can we use false? So thing is, we need to zero center our inputs and our output vector before passing to the model. If you are going to use the false parameter, so we can zero center the input and output vector. So mean x mean equal to x train dot mean axis equal to 0, y mean equal to y train dot mean. So you have to zero center both x and y. So we will fit with the centered data. So now this should work. Okay, as you can see, we still don't get the correct value as sklearn. This model is still probably underfitting. Why? So what we need to do is, when during the inference time too, we have to find the mean and then get the predicted value. So for x test, we have to find its mean. Okay, still it does not work. Why? Because Even in the output we have to use the y mean and get our value back. So the value will be out whatever predicted plus y mean. So now we can get the actual values that we used to get earlier. So one thing to remember, you have to find the average of training data set and then use that statistics for the validation and tested data set. You should not calculate new average and new mean for the test and validation data set. That is very important. So I have used x mean that we found from the training data set, y mean that we found from the training data set. So this should be careful. So in scenarios where the data is already zero centered, you can actually pass the parameter false and do the calculation in its closed form equation. So this is the only scenario where we will need the false parameter. So hope you guys understood the closed form equation implementation. So we implemented closed form equation. We handle for singular matrices. We also used a least square function. We also used the zero centering mechanism that is actually implemented in scikit-learn. So I hope it was very useful. So till the next video, bye.